Good morning, everybody. Welcome to another week of Chem 103. Today we're going to talk about ions and ionic bonding, and this will help you out. Even though we're not doing an assignment on this week, this will help you out with the quiz that's coming up, as well as some of the labs too. So, won't be super long today, but I did want to show you some things that you should know about dealing with ions. So, let's get started. As usual, if you have questions, just leave them in the chat, or you can also send them to the Discord in the live stream channel. Right. So, up to this point, we've always been, when we talk about molecules or just chemical compounds in general, we've been talking about these kinds of what we call covalent compounds or molecular compounds, compounds where we have, like carbon and then connected to some hydrogen and some other stuff. Whoops. My pen got messed up there. Okay. These kinds of things where they're connected, and then we approximated those with line structures and condensed structures. Half of you had a quiz on that last week, and half of you it'll be in lab this week. So those are organic structures. Those are molecular structures. Those are structures made from atoms sharing electrons. Ions and ionic bonding is a little bit different. So this is most commonly seen with things like metals. So if we have, let's say, a sodium atom, Na, sodium doesn't make these kinds of bonds the way that carbon, hydrogen, oxygen do. Instead, sodium, when it becomes, it can exist in just its elemental state, just sodium, which is a metal, that would just look like that. But another way that it can form compounds is by becoming an ion. So when sodium becomes an ion, it loses an electron to become sodium plus 1. So sometimes we then say, okay, that electron is one of the products. So this is what we would call a sodium atom, and then this is a sodium ion. Notice we haven't changed the name here, but it was an atom and now it's an ion. And we did this in that atoms activity from a couple weeks ago. So if you're not clear on how that works or why it's positively charged when it loses an electron, go back and check that or watch that video again when we talked a little bit about how to make ions and what ions involve. But this is now a sodium ion. It has a positive charge because it has an imbalance of electrons and protons. So it lost an electron, now it has one more proton. Now this totally changes the properties of these things. So sodium itself, neutral sodium is, as I said, a metal. It's soft. You can actually cut it with like a butter knife. It's also highly reactive with water, even water in the air. So you may have seen, you can look up videos of people throwing sodium into bodies of water and it kind of like explodes because it reacts with water to make hydrogen gas. Sodium ion, on the other hand, by losing that electron, this is now the sodium that's in salt. So when we look at sodium chloride, which we'll be using for an example today, again, not explosive anymore, and in fact, something that you need to eat, that we all need for our bodies to function. So losing that electron changes things a lot. On the other side, we could take something like a chlorine atom. Chlorine doesn't really exist much in its just atomic form. It's usually known as a diatomic molecule, so Cl2 is chlorine gas. And chlorine gas is a poisonous, really nasty gas. But that's the elemental form of chlorine. And chlorine doesn't lose electrons like sodium. Chlorine gains electrons. So chlorine can gain an electron and become Cl minus. And now we call that a chloride ion. Notice now the name has changed. So for negatively charged ions, the name changes. We drop the suffix and instead say "ide." Instead of chlorine, it becomes chloride. Okay. So then when these ions come together, we're going to talk a little bit more about how you can tell what charge an ion gets. But let's first talk about what happens when ions come together. So it turns out that positive ions, negative ions can't really exist individually. They actually have to come together to form a compound. And that compound overall has to be neutral. So if we have a sodium ion and a chloride ion, they can make this compound sodium chloride because +1 and -1 ends up canceling out and making everything neutral. So NaCl is a neutral compound. All right, so we're going to talk about ions first here, and then we're going to look at ionic compounds. So the compound is when the ions come together. The ions are just the ions. All right, a couple terms that you need to know. A cation is a positively charged ion, and an anion is a negatively charged ion. So like that sodium plus that we saw is a cation. That chloride that we saw is an anion. And we can figure out not only if a particle is likely to be a cation or an anion, but also what the charge is likely to be from the periodic table. So let's take a look at the periodic table. Here it is behind me. You'll notice there are some column numbers up top above the groups there. You see the column numbers. Now there's a couple different ways to express those. You'll see there's like a 15 on top. So let's take this one here with nitrogen in it. It says 15, and then it says VA, and then it says 5A. So 15, the newer way of labeling the columns is just 1 through 18 from left to right. The older way of doing it is to have A's and B's and have like 1A, 2A, 3A, 4A. So you'll notice that the far left two columns are 1A and 2A, and then all these ones behind my head here are 3A, 4A, 5A through 8A, and then the ones in the middle over here, these light blue ones, are the B's, and that's because they have a little bit different properties. So most periodic tables still actually use both numberings, and so you'll see that. But we can actually use this to help us figure out what's going on with ions. So the first thing to remember is that metals tend to form cations and nonmetals tend to form anions. And remember that this green area here is the separation between the metals and the nonmetals. So everything over to the left is metals, everything to the right of that is nonmetals. And that means that for our purposes, and of course there's always some exceptions, but for our purposes, all those metals over to the left are going to form the cations, and the nonmetals over here are going to form the anions. We can use the proximity to the end of the table, to each side, to actually figure out which metals are going to form which charges. And this has to do with their electron counts, and you can read into that and learn about that if you want. But for our purposes, for our class, the important thing is that certain areas of this table, we always can predict the charge of the ion that's formed. And it looks something like this. So let's go back to our document here. This is also in the reading, by the way. So if what I'm saying isn't making sense, you can check it out in the reading. All right, so here's our periodic table. Here's hydrogen, here's helium, and so on. I think I did that right. Yeah. So the areas we're going to focus on are the first column right here, the second column, the third column. Actually, it's just one little spot in the third column right here. We're going to skip the fourth, and then we're going to look at the fifth. I made my thing a little bit too skinny here, the 6th and the 7th, and we're going to ignore the 8th for now too. Okay, so for each of those columns, let me number these just because it's going to get confusing here otherwise. So here's column 1, here's column 2. This one is 13 or 3A, and then we've got 15, 16, and 17, also known as 5A, 6A, and 7A. So column 1A always makes +1 ions. That means when you take a neutral atom from that column, it's going to lose an electron and become a +1 ion. So if we want to know the charge of any ion in that column, if it's an ion, we know already it's going to be +1 just because it's there. So if I said, hey, what's the charge of a potassium ion, which is K, you find it on the periodic table, you notice that it's in column 1, and you go, oh, K is a +1 ion. It has a charge of +1. It's missing 1 electron. If we go to column number 2, we've got +2 ions. So again, if you saw a formula or something like that and you saw a calcium ion on it, you'd look up calcium, you'd find that its symbol is Ca, that it's in column 2A, and that would tell you that it is a +2 ion. So other ones that are predictable like that, in column 13, there's just aluminum, because that's really the only metal in there that does this. But aluminum is always +3. And then column 15, I should have made this bigger. I'll just draw arrows. Are -3, column 16 -2, and column 17 -1. Notice also, when we write the charge on the ion, sometimes we put the number in front of the. Some people like to put the number in front of the charge. Some people like to put the number after the charge. It doesn't really matter. Either one expresses the correct information. I usually put the number in front just because then it can be a little bit less confusing if you have multiple things together. But either way is fine. All right, so back to the periodic table. Let's interpret that again. So the column to the far right, these right here, these are the noble gases. These don't really make ions, so we can just ignore those. Then the next column over, those are the halogens. Those are called the halogens, and those are generally -1 ion. So you'll see chlorine there, which was our example from before, makes a -1 chloride ion. And then the next one over here, we've got -2 ions. So like when oxygen makes an ion, it makes an oxide ion, which is -2 charge. And when these nitrogen, phosphorus, and even sometimes some of these lower ones make ions, they will be -3. So by that pattern, we would expect the next column to be -4, but when we get to 4 + 4 minus, that's kind of gets to be pretty big charges. So we don't really see that a lot. So we don't usually consider that in this category. Okay, so that means everywhere else on the periodic table, all this stuff in the middle and down here, those are not predictable charges. We can't simply say, oh, you've got some copper. What is the charge? Let's see, it's in column 11, whatever. It doesn't work. Many of these elements make multiple different possible ions. So they might be like copper, for instance, can be +1 or +2. Iron, Fe over there, can be +2 or +3. So it no longer is predictable, and we'll talk about what to do with those in a minute. All right, hold on. Cat, who's about to knock some stuff over. All right, well, we'll see what happens. Okay, so that's how you determine the charges of various ions based on the periodic table. Let me get rid of this image here. So from there, we can look at ionic compounds. So armed with that knowledge that we just talked about, and with what we said before, that compounds are neutral sets of cations and anions together, we can figure out ionic compounds and what their formulas should be and write them down. So let's do it like an example. So let's say I wanted to know the formula for this ionic compound, potassium oxide. Potassium oxide is a compound, an ionic compound. We can tell it's ionic because it contains a metal and a nonmetal, and we want to write down what the chemical formula for that would be. So to do that, we need to know the symbols of both of these ions, but we also need to know their charges, because depending on the charge, they may have will have different ratios to be able to be neutral. So first, we look these things up on the periodic table. We look up potassium, and we look up oxide. Isn't really there by that word, but we know that we just changed the end, so we can assume that's going to come from another element that starts with ox, which would be oxygen. So we look these two up in the periodic table, and we see that potassium is K and oxide is O. Also keep in mind that you'll always have the periodic table with you. It would always be accessible. So if you don't know the names and the symbols of these elements, that's fine. The point is to look them up and you find them. So we find K and we find O. All right, so here's where we have to do a little bit of work. We can't just stick those together and say the formula for potassium oxide is KO, because that may not be how those ions combine. In order to do that, we need the charges of the ions. So it's not enough just to write the symbols. We also need the charges. So let's look back at our periodic table and find those charges. So we can see potassium all the way over on the left. That would be in column 1 or 1A. And that tells us that the potassium ion has a charge of +1. All right. And then we can find oxygen, which is right above my head here. And that is in column 6A. And we know from earlier that those all make -2 ions. So we can write -2 or 2- for this one. So we have a +1 charge on potassium and a -2 charge on oxygen. So we can put the compound together now, but we need to adjust the ratios of potassium and oxygen so that the overall compound is neutral. And what that means is that we need another potassium ion. So we have 2 pluses and 2 minuses, and now we have a balanced compound. So notice when we add 2 potassiums, we now have a total of +2 to balance our total of -2 over here. So the way we would write that is K2O to indicate that we need 2 potassiums for every oxygen. And that's our potassium oxide formula for that ionic compound. Okay, let's try another one. Aluminum chloride. By the way, aluminum is also sometimes spelled aluminium. It's just a different variation. That's also okay. So we look these up on the periodic table, and we find that aluminum is Al and chloride is Cl. Once again, we need their charges so we can put them together in a compound. So we find aluminum in 3A right here, making its charge +3. We find chlorine over here, making chloride a -1 ion. So +3, -1. And then in order to balance these to make an overall neutral compound, we need 3 of these so that we have a total of 3- to balance out the 3+ on the aluminum. And that means that our compound is going to be AlCl3. Right. Any questions on those so far? Okay. So let's talk about what happens now when we have the other metals. Remember I said in the middle of the periodic table, there's all these other elements all these other metals that don't have what we would say is a predictable or known charge. So iron, for instance, can be either +1 or +2. So when we express those compounds, right, they're always expressed in this way. So instead of just the name of each thing, like aluminum chloride, there's this extra little piece, which is this number in Roman numerals in parentheses right after the ion. And what that number tells you is not the subscript, not the ratio, but the charge. So when we have that number there, now we know, we look up that iron is Fe, and this tells us that it's actually Fe plus 3, or 3 plus. See that there? So that 3 means that 3 plus. And then the chloride is still the same chloride as before. So we have a 3 plus and a 1 minus, and that means that our iron 3 chloride is going to be FeCl3. Now the most confusing part about this, the thing that I see wrong most, is people mistaking this number for the subscript. The subscript here, notice, is 1. It's not 3. The 3 in parentheses gives us the charge on the ion, not the subscript in the formula, because depending on what the other element is, that subscript could change. So for example, rust, like when your car rusts, rust is iron 3 oxide. Let's put that formula together in the same way. Iron 3 is still Fe3 plus. So anytime we see iron 3, that's iron Fe3 plus. If there were a different Roman numeral in here like 2, then we'd say 2 plus. And then we get oxide from our periodic table just as we did before, O2 minus. And now notice that's not going to be, there's not going to be a 3 here, right? Because these have to balance. And this is actually one of the times it gets a little bit tricky to balance. To balance a 3 and a 2, you have to actually change the amounts of both of them so that you end up with 6 plus and 6 minus overall. So if we take 2 of these and 3 of these, we now have 6 plus total over here and minus 6 total over here, 6 minus over here. And the way we would write that formula is Fe2O3. All right, so notice iron 3, same ions, but the formula is going to be different when they're paired with different anions. Same cations, different anions. All right, so keep in mind when you see those parentheses, that's the charge on the metal, on the cation, not the subscript in the formula. If you remember that, you'll be okay. Okay, so now we've built 2 different types of compounds. Compounds where we know the charges based on the periodic table, and compounds where we don't know the charges, but we're told the charge in the formula. Our last category of the ionic compounds are going to be the compounds involving what we call polyatomic ions. So all of these ions that we've seen so far are what we would call monoatomic, meaning they only have one atom. So you've got a potassium ion, it's just K. You've got an oxide ion, it's just O. You've got a chloride ion, it's just Cl, and so on. But there are also ions, common ions, that are made of multiple atoms. So I'm going to list some of the common ones here. In other chemistry classes, these would be required to be memorized, but for our purposes, I'll always give you these. I'll give you a table of them if you need them. So we have ones like nitrate, which is NO3 minus. sulfate, SO4 2 minus, phosphate, which is PO4 and has a charge of -3. Some of these we've used in lab already, like hydroxide and sodium hydroxide, which is OH with a charge of -1. Then we've also there are many. I'm just gonna put in a few. Carbonate, CO3 -2, and there's actually some positive ones as well, like ammonium, NH4. So with these polyatomic ions, they have a particular formula and a particular charge, but when they're used in compounds, all the stuff we've already done still applies. They still kind of work the same way. So you can have, for example, sodium sulfate, and you would write down your ions. So sodium is still Na+. Sulfate now, we can't get from the periodic table. The just S2 minus on the periodic table would be sulfide. But when we see that 8, that's the clue that it's a polyatomic ion. So we would look it up on our chart of polyatomic ions. And we notice that sulfate is SO4 2 minus. So we write that down, SO4 2 minus. And then the rest of the putting the compound together works just as before. We need 2 of the +1 sodiums to balance the -2 sulfate. And that compound ends up looking like Na2SO4. Sometimes we have to change the number of the polyatomic ion, and that works the same way. The only difference is we have to use parentheses so that it's clear. So for example, calcium hydroxide. Calcium we look up on the periodic table. It's in column 2, which gives it a 2+ charge. And then hydroxide is on our list here, so it's OH with a -1 charge. And we notice here that the calcium has a higher charge than the hydroxide, so we need 2 of those. 2+, 2- total now. And the way we write that formula then is CaOH2, and the OH has to be in parentheses, because otherwise, if we wrote it like this, it looks like there's 2 oh, you can't see that, sorry. If we wrote it like that, it looks like there's 2 hydrogens, but only 1 oxygen. So we can't do that. So I'll cover that back up. We want to do it like this so that we know there are 2 of the whole hydroxides. This works with the other types of ions too. So for example, we can have copper 2 nitrate. Copper 2 is Cu plus 2. Remember the Roman numeral gives us the charge. So if it's a 2 there, that tells us it's a +2 charge. And then nitrate is NO3 -1. Again, there's no like shortcut from the periodic table to get that charge. It's just that's how nitrate is defined. Nitrate is NO3 and has a charge of -1. So you can either memorize these or you just consult your list. And then once you've got the formulas, we can see that we need 2 of the -1 nitrates to balance the +2 copper. And so our final formula for copper 2 nitrate looks like this. Notice that we need parentheses around the nitrate to show that we have 2 of them for every copper ion. All right. So besides the parentheses, the other thing that I see sometimes errors with polyatomic ions is just people not recognizing that they are in fact different and they're not on the periodic table. So if you take something like ammonium chloride, so I'll ask you like on a quiz, write the formula for ammonium chloride. And I'd give you a list of polyatomic ions. Remember, I said you don't have to memorize them. we have to know that ammonium is one of those polyatomic ions and that its formula is NH4 plus. And I've asked this before. I've asked this question before, or ones like it, and I always get somebody who just like takes a guess and makes it Am. And Am is actually an element. It's way down here. Yeah, right there. But it's not ammonium. It's americium. So that is not right. Again, use your references. Look up your stuff on the table. Look at the names on the periodic table. You don't need to just guess. And then chloride here is Cl minus. So this compound, 1 plus 1 minus, we don't need to change the ratios. It just ends up being NH4Cl. All right, any questions about any of that stuff? Okay. Well, if questions come up later, please let me know. Remember that the goal here is that you can look at these names and figure out what the compounds are. This is important because, like in lab, for example, the bottles of chemicals may not have the formula, they may have the name. But in your notebook or in the lab instructions, it may have the formula and not the name. So being able to understand what both of those mean is important. Now notice what we did not do today is we did not start with a compound and then figure out how to make the name. That is not an objective for this class. If you want to learn that, that's fine, but that's not something I would ask you to be able to do. What I do want you to be able to do is look at a name of an ionic compound and figure out what the formula is, what the ions are that are in that formula. All right, so all the things that we did, all the examples we did today, those are the kinds of things that I would want you to be able to do. Again, you don't have to memorize anything really with this. You just have to use the periodic table or a list of polyatomic ions and then put those compounds together so that their charges are balanced. All right, so that's it for today. If you have any questions, just send them my way, and I will see half of you on Wednesday and the rest of you the next week. So, bye, everybody.